Good morning, everyone. This is Martin Jean with Careerform Engineering. Thank you for joining us today for the technical webinar. Today, theme will be tolerance analysis, an effective method for validating product design. For those who, some of you know us already. Some of you have been there maybe on the previous webinars we've done on the topic. So this is the third of a series. And we're really glad to have you today. It's always fun to do those webinars. There's still some people joining in, so we decided to start right away, but we're still waiting for a few other people to join in. So I'll take some time to introduce myself. Well, I'm a mechanical engineer. I've been with Careerform for about 13 years now. I've worked in metrology and stress engineering before, so this is kind of my background, and I'm responsible at Careerform Engineering for business development and the project management team. So this is what I do. But the person that will be presenting the main topic today is Marc Lépine. Marc is actually our responsible for the DM team at Careerform Engineering, so we're really glad to have him today. And he's really, he has a really great knowledge in the dimensional management, so this is going to be a good session for you guys. Marc he's a mechanical engineer himself also. He has about 10 years experience, and he has a master degree actually in dimensional management, and he's worked in the aerospace industry and the transport train industry before. Been with Careerform, and even with Careerform Engineering, actually, he's working pretty much with these industries, so buses, trains, and aircraft. So this is the main areas where we apply our knowledge in dimensional management. So Marc, hello. I don't know if you see him on the camera. And actually today, the last two webinars we've done was pretty much like a 30-minute webinar. Today, content is a bit more heavy. It's a bit more longer. Heavy. Heavy might not be the proper expression, but it's a bit more dense. So there's a good level of material. It's really interesting, but it's a bit longer. So we'll try to keep it as fast as possible. So in terms for the agenda, so you can expect maybe a 45-minute presentation. I'll start by presenting Careerform Engineering for those who might not know the company. After that, we'll go in the context of why dimensional management and what is GD&T and everything, and then we're gonna get into the core presentation of today, which is like a basic variation analysis. So we'll go through somehow a case study or a simple analysis, and then we'll have also like a more advanced analysis using more advanced softwares, and then we can have the question period. So all along the presentation, you guys can ask questions on the GoToWebinar tool set you have on your screen. We see those questions, but we'll answer them most probably only at the end of the presentation, so that everybody that wants to leave before the question period might do so. So we'll keep all the questions and we'll go through that after the presentation. So, and also at the end of the presentation, and this is important, there's a little survey when you close the window. So please take the 2 minutes it takes to give us your feedback. We really appreciate that, and we take the comments and everything you put in there to develop better content for the next webinar. So please take those 2 minutes. We really appreciate it. What is Careerform Engineering and what is Careerform itself? Actually, Careerform Engineering is a division of Careerform. We're about 185 technical experts, mainly in mechanical engineering, electrical engineering, and all kind of affiliated capacity or professions. We have 4 offices in America, 3 in Quebec province, so Quebec City, which is the headquarter, Montreal, and then we have St. Clair, which is a little smaller office, and then we have Irvine in California, which will serve the American customers. And Careerform is, some of you might already know Careerform, but Careerform Engineering is a division of a larger company called Careerform, which is about 700 employees, and that develops metrology technologies. And it's part of a larger corporation, which is called Amitech. And Amitech is a US-based public corporation with about 50 business units, similar to Careerform, that develops technology and different kind of products that contents that with a high level of engineering content, actually. So B2B products. So what does Careerform Engineering has to offer? We want to go with this slide before going into the presentation, just before put you in context actually what is dimensional management, how it puts itself within all the product development process and the business we do actually. So Careerform Engineering, we like to say we're kind of a catalyst for our customers. So we develop products, we accelerate product development, and we help with different expertise to tackle different challenges you have, companies have when they go through product development and industrialization of their products. So we start from the idea, so we can take your idea and have an industrial designer to go over and sketch stuff and just start drawings, ideas, and how it should look and how it should function. And then we have different type of service that come along with that, reverse engineering, prototyping. So everything which is related to advanced engineering, that's how we call that. So we like very preliminary design of products. And then the core of what we do in terms of time and effort would be more into the engineering portion. So once we know exactly what we want to develop, and that's where you put all the energy in the engineering. So mechanical, electronic, electrical, automation, when we design machines. And then dimensional management, which is today's topic, which works with all these different expertise we have. It's really an expertise that works with all the others, so it's really cross-functional. Project management, and then the simulation team. So we have 20 people in the simulation team that does only simulation, mostly for stress engineering, but also for fluid dynamics. So we can simulate airflow, water flow, and then structural behaviors. And then we can also do everything related with testing or making coupons to get the proper data to make simulation correlation. So if you don't know how your material is going to react, we can make a test and then put that in our simulation software. So we have all kind of tools and expertise to predict behaviors and predict also variation in dimensions. So when you develop a product, it's always good to have a good insight on what's the product going to look at the end. So what we've been through previously, for those maybe who weren't there, there has been 2 different webinars in pretty much the same topic, which is dimensional management. The first one was explaining pretty much like the whole, in general, the different 6 steps we call that for dimensional management. And then there was a second one, which is more about how to define functional datums, reference frames. So pretty much the basic of how you should start working with datums to get further on with all the other topics on the dimensional management. And then today's topic, which is variation analysis. So if you missed those 2 ones, it's available on our website, so you can always go there and listen to the webinar, which was recorded as it is today. So also today's webinar is going to be recorded. So if there's any, I mean, you have a phone call and you miss 5 minutes, don't worry. You can go back and on your website and check the few slides you might have missed there. So it's going to be available. I will send you an email to give you the link. So from here, I'll leave you with Marc, which has a lot of stuff to show you today. So you can go ahead, Marc.
Yeah, thank you, Martin, for the nice introduction. As you mentioned, you talked about the survey, and I wanted to bring back some type of questions we had from the 2 first webinars. We had a lot of questions about, for example, how do you define logical tolerance values, or how can you, let's say, give some large tolerances but keep the functionality of your product. There were a lot of questions related to tolerance analysis, and this is why we found adequate today to talk about really tolerance or variation analysis. Variation analysis, let's see if we try to put a definition on this term, is really the study, let's say, of the effects of your parts, dimensional variation or tolerances on the product assembly. This is the nice and long definition. What comes in my mind for when I think about variation analysis or tolerance analysis, it's a little bit more, let's say, simpler and maybe less attractive. It's a simple tolerance stack up. Most of designers or mechanical engineer already touched to this subject. But when it's, let's say, when do we apply it? But it really becomes interesting when you apply it to, let's say, a product that needs to be assembled on a manufacturing line. When you develop a product, tolerance stack-ups are used. They're used for several reasons, but two good reasons. First one is really to define the functional tolerances. What will be your GD&T? What are your needs based on your product requirement? Functional tolerances meaning that you don't want to go all over your product with tight tolerances, which will increase the cost, but you really want to pinpoint your critical dimensions and tolerances that really affects the functionality or assembly of the product. So this is a really interesting first point, but the second one is also really interesting. It's when applying tolerance analysis, let's say in the early design stage, we are able, let's say, to find some problems and solve them quickly before having or before leaving the problems on the assembly line. It's kind of helps to optimize the design. And I'm making a kind of a comparison here with another, let's say, type of analysis in the mechanical engineering field, which is the finite element analysis. When you do the FEA on a product, what you want to do is really validate the strength or the resistance of your assembly before the physical testing. So, and when you're looking at the process, you start by defining inputs. You say, okay, I have a design, I have some materials, I have some, let's say, some boundary conditions between my parts, I have some load cases. I take all this information and I put this into a mathematical model which will allow to simulate the usage of the product, and we can see if we have some stress or some failures around this design. And based on the results, we can decide, is this acceptable or do I need to make some changes? So when you capture this before having the parts, you can modify your design and then release this design and having a really good, let's say, confidence that your assembly or your product will fulfill the requirements. If I come back to, let's say, variation analysis, process is quite similar. But what you want to do is validate the assembly before having the physical parts. So if we look at the inputs we have for your product, you have your parts which have a manufacturing process with it and have a process capability. You have a build sequence, and you have, let's say, some requirements that you want to fulfill. So you take all this information, you create a small mathematical model, and you do the tolerance stack up, which will give you some results. And based on this, you are able to judge, okay, am I okay with this, or do I need to make improvement to my design? Do I need to add adjustment? Do I need to have more clearance between parts? Do I need to tighten some tolerances? And once this is made and that you are pretty confident, then you can release all your parts and make the physical assembly. So this is a really nice application of tolerance stackups. But the big question here is, and this is the question we'll try to answer during this webinar, is, okay, how do we do this? There are really several tools available for the tolerance analysis. I'm bringing here just a few of them. If we look, let's say, on the left side of the screen, talking about bolt pattern calculation, this is quite a simple calculation that is really used when you have, let's say, two plates and you want to fasten them together. You want your oils to line up. This is the kind of calculation you'll do. But today we'll try to focus more on let's say, on the basic variation analysis, which is, let's say, a really accessible tool for almost every designer and every mechanical engineer. It's quite a fast method when you have some simple designs you want to validate, and it's really flexible, meaning that you can apply this to every kind of assembly. So it's really a nice tool that you can almost, let's say, have a piece of paper, a pen, and on the side of the table, just start to calculate or evaluate your tolerance stack up. I'll take some time at the end of the webinar to talk about, to introduce, let's say, the advanced variation analysis, which have some really nice benefits when things get a little bit more complicated. So before starting, let's say, every tolerance analysis, and this is true for the basic or the advanced analysis, And there are several things you need to know. First one is how is your product assembled? Um, for those of you, this may seem like a, a simple question, but when products are, let's say, a bit more complicated and jigs, fixtures, adjustments start to come into play, um, the assembly method is not that clear. So for the example we have today, I'll just try to recap how this thing is how do we want to assemble this suspension system. So you have several parts. You have a yellow mainframe on the left side, and this is the base of our assembly. This is the starting point. So on this, we'll bolt, we'll attach a subframe, which is a big part in gray, which contains all the attachment points for the suspension system. So starting from there, we'll install, let's say, the red arm, the lower arm, um, onto the subframe on the lower point, and then we'll install on it at the ball joint the knuckle, which is the kind of brown part on the right side. So once you're there, the knuckle is kind of located, but it needs to be oriented. It needs to be locked down in rotation. So this is the role of the upper arm, which is attached to the subframe again, but you have another ball joint at the top over there that attached to the knuckle. And then finally, within the knuckle, you have really two important parts, which is the spindle, which really supports all the wheel assembly, and on it comes the wheel bearing on which the wheel will be attached. So
Yeah, and Mark, if I can make some, yeah, if you can, you stay, yeah, on this slide, if I can make some extra mileage on what you said, Mark mentioned that it might be a simple question for you, for people in the industry. So, well, how is it assembled? So now what we see on this screen is how it is assembled functionally, like the suspension. But Mark comment is more about like it's one thing for the engineer and the designers that are on the R&D side developing the product to think about how it is assembled for to function properly, but then it's all another story when it gets to the production line where they need tools to assemble that in a really high production rate. So they're gonna use some different kind of equipment to assemble that, and then you have to think about all these constraints when you're gonna go through your design actually. So your GD&T and all your variation will be taken into account. So I think that's kind of what Mark wanted to say. This, it might seem simple, but actually when you think about all the constraint and that's going to come into play, it's not that simple.
yeah, that's a good point, Martin. And I mean, even on the tolerance stack up side, even if there's just a simple jig implied into the assembly of this thing, then probably that you have to consider it into your tolerance stack up. So this is really important to have a good knowledge of this assembly method. The second, let's say, big input before doing tolerance stack ups is, okay, what are the requirements that I need to analyze? On a complex product, you have lots of requirements. Sometimes the reflex is to really, okay, I'll just analyze everything, but it's becomes really a high volume of analysis and you don't really have the quality you should have. So the important is really to focus on the, let's say, on the critical characteristic or the key characteristics that affects, let's say, really your assembly on your manufacturing line, but also, let's say, the customer satisfaction regarding your product. So if we take one of those requirements for the webinar, we'll take the most simple one, just to start everything. Let's say we have a requirement here that is the position, let's say, of the wheel mounting surface relative to the center of the vehicle. So looking at the picture, I mean, the requirement is pretty much well defined. You have a direction, you have a target, you have an acceptable target of plus minus 4 millimeter, but still there's a little problem in this picture is that the center of the, let's say, of the vehicle, you don't know where it is. Is it the which hole into the mainframe is it, or is it the hole at the top? I'm using this example just to bring a small rule when doing tolerance stack up is um, you really need to hang on, let's say, physical features or functional features that are used on your assembly line. For example, this kind of vehicle, most of manufacturing line have a final station when they verify all the alignments, all the wheel angles and position. And to do this, they have a tooling that attached to a reference hole. So your tolerance stack up should ideally start from this same tooling hole that is used as a final for final verification. So a small detail, but it can help a lot to give more precision to your tolerance stack ups. So once your requirement is really clear, then you start the exercise. The goal here is really to find, let's say, all the links, all the physical links that that gives a relation between your starting point of your requirement and the finish or the arrival of the requirement. So starting, let's say, part by part, if we look at the first part here is really the main frame, then you start from your tooling hole that you know that is used, and you go to, let's say, the first link would be, let's say, the holes that are used to attach the subframe. So regarding this part, you know, this for information, this part is a welded assembly. It's quite a large part, meaning, I mean, it's the frame of a vehicle. So based on your knowledge of the, or even your discussion with the supplier, if you already have them, you can already think of some kind of tolerance that is, let's say, easily achievable by the supplier. So for this kind of feature, you already know you have, let's say, some kind of position tolerance, and you know that it won't be precise as if it was machined. I mean, those tubes are welded together, so you want to give, let's say, the tolerance that reflects the process capability. Here is, for example, we have a plus minus 1.5 millimeter, which seems quite achievable on this kind of part. And I'm bringing here a second rule, maybe, not to forget. This one is quite simple, but sometimes when things get complicated, we sometimes forget it. But on a part, when you want to, let's say, move from one feature to the other, just remember that you always have to consider some kind of tolerance or variation on the part. So if I'm continuing my way up to the finish point of my requirement, we are now, let's say, into the hole of the mainframe, and we want to jump to the, let's say, on the subframe. Important thing when you want to jump from one part to the other is there has to be some kind of physical link or variation between the two parts. For example, here on the mainframe, we have a hole which will, it's not within the design, but this kind of information when you do the stack up, you have it not too far. There's a hole that is used to install a reeve nut, which will be threaded in a 10 millimeter bolt, and you have a clearance hole on the subframe, let's say a 2 millimeter clearance. But this clearance, when you look at it, affect directly your requirement, meaning that all your subframe can be stacked all the way to, let's say, the left side at plus 1 millimeter, and then on the opposite side at minus 1 millimeter. So your clearance affects the requirement, and you need to consider this in your tolerance stackup. So now that we are on, let's say, the subframe, you continue your way to find, let's say, the path to the final requirement. We are into the mounting holes, and we want to go to, let's say, the lower arm mounting points. Same reflection. We have let's say, a welded assembly. This won't be that precise, but okay, the two holes are quite close together. Supplier tells me that there will be a jig to locate the two together. Okay, so I'm okay to, let's say, to give a plus minus 1 millimeter tolerance on this one. So, and the idea is really to go part by part and find all the links, and that will bring you to the end of the requirement. Another example maybe here, okay, so we are in the hole of the subframe. We want to go into the, let's say, the lower arm. Let's say you don't have all the information in the design. Design is not finished or anything. You see, we don't have the bolt, we don't have the bushings, we don't have all the information, but you know that like functionally for this kind of assembly, you don't want that much play or clearance into this hole or into this assembly of the lower arm. You know there will be some kind of shoulder bolt and a really tight bushing. So at some point we can make some assumptions into the tolerance stack-up. So the important, let's say you say this play or this clearance will be 0. Important is just to still keep it into your tolerance stack-up so that you remember that you've made that assumptions. And if for some reason at some point you think that this clearance will affect the requirement, then you can easily add it afterwards or just change the value. So I'm going a little bit fast forward here for the next ones. I mean, you really need to just find the links. Let's say if you have the lower arm, you have the notion of position of your ball joint relative to the attachment points. Once again, same reflection. You need to consider process capability on this kind of assembly. You give a tolerance plus minus 0.75 for this one. Then I come into my ball joint assembly on my knuckle. Once again, we can make some assumptions. This kind of ball joint has, I mean, almost 0 clearance. It's a really tight fit. So we can make the assumption, okay, this won't affect that much my requirement. I'm continuing my way. I'm in the knuckle. I need to have a relation between that ball joint position and, let's say, the mounting or the mating surface of the spindle. Now we've changed process. I mean, we were on welded parts. Now we've jumped onto a machine part. So you see the tolerance that comes with it. We've just reduced the tolerance based on process capability over here. So if we continue, we have the spindle, which is mated on the knuckle face. It's a machine part. Once again, you see the kind of tolerance we can give plus minus 0.1. And defining that value is really at the beginning of the design, and you didn't have the discussions with your suppliers. I mean, you can find quite easily the process capabilities of different kind of manufacturing processes. So these are some assumptions, but when you start sending some preliminary drawings or we have some discussions, you can quickly ask your suppliers, okay, I have this kind of part, what kind of accuracy you think you'll have, and you can update your stack up quite easily. So just to finish the stack up to arrive at the final phase, we have a last dimension, which is the wheel hub, which is, once again, a machined part. So you have the tolerance of plus minus 0.2 millimeters. So once you've reached, let's say, your final point, you can just recap all those links that makes your stack up, and you bring them into a little table. So you have all your parts or assembly steps, you have all the features, and then you have all the tolerances that you've defined. And you can, let's say, do the little picture, let's say, on the right-hand side, and see that, okay, here are all my contributors to the requirement. But if you take a closer look at the picture, at some point you can question, okay, did I get all the effects? Because for this kind of assembly, which have 2 arms at an angle with a kind of a long knuckle that protrudes down the main frame, there's a lot of rotation or 2D effects. It's at this point, it's possible to add them into the stack up. It's a little bit complicated, but here's how you can do it. If we take, for example, the lower arm, lower arm is at an angle in reality, and let's say the dimension, the tolerance I gave to this arm, if you put it on a drawing, you won't put it, let's say, at an angle of 12 degrees. You will put it, let's say, in the plane of the lower arm. So what you have to consider is how does my lower arm how much of an effect does it have to the total variation of my requirement? So here comes, let's say, the notion of weight. So you have a tolerance plus minus 0.75, but in reality, because of the angle and because your requirement is in the y direction, you don't have a one-to-one effect. You have it's almost one-to-one here because you're at 12 degree. In reality, you have a 0.98 weight to this to this tolerance. Maybe another one, just to give you another example, the upper arm. When you look at it, if the upper arm varies in length, your knuckle will try to rotate around the ball joint that is on the lower arm. So the tolerance on this arm also affects the requirement. And the weight that is associated to it, you have the angle, which is similar, let's say, to the lower arm, but you also have kind of projection effect because of the difference in, let's say, because of the length of the knuckle. So in reality, your plus minus 0.75 tolerance of the upper arm has an effect of plus minus 0.9 because your weight is at almost 1.2. So capturing all those 2D effects, this is where the basic variation analysis becomes a little bit more complicated. It's feasible, but it's a little bit more tricky to capture all the effects. So I mean, if you are confident with your model, you think that you've captured most of the effects, then you can just update that little table. I added, let's say, at the bottom, my upper arm, which becomes item 10 with its tolerance. But I also added let's say, the weight column, in which you see all my contributors that are in the exact same direction with my requirement. I have, let's say, a weight of 1, but you see that my item number 5, lower arm, has a weight of 0.98, and my item number 10 is 1.18 because of the projection of the knuckle. So once you're confident with your model, then it's time really to stack up those tolerances. So you take all your table and you'll do kind of a weighted sum of all those tolerances. Here there are, once again, several ways to do the sum. The first one and the most popular is, let's say, the worst case. I mean, the title says it all. It's kind of a pessimistic scenario, meaning that, let's say, all your parts will come at the limit of their tolerances, let's say, in the same direction at the same time. So this is really a bad a bad scenario. In real life, there's a random behavior behind all this, and this is where the statistic approach is used. If you look down at the statistics, this sum states that takes the assumption that all your, let's say, your parts will normally be close to the nominal, meaning that most of the parts will be really good, close to zero deviation, and few of them will be at the worst case. So when you do the sum, you have some really good results or better results than the worst case. But once again, there's a big assumption behind this one, is that all your parts are really close to the nominal, which is not true for a lot of processes. For example, the welded assembly, sometimes you have a deformation or shrinkage due to the welding. So all your parts may be closer to the minus. Some other processes have parts closer to the maximum. So this is where the expanded statistics is used. It's really, you take your statistic result and you expand the interval by 1.5 to give you kind of a safety factor to account with those shifts into different manufacturing processes. So if I take those
Hey, Mark,
approaches,
before
yeah,
going to the issue, can you go back 2 slides up? I mean,
yeah, sure.
So if when I look, I mean, Mark is definitely like the specialist, but when I look at even the slide before, if we, I'll just, there's two different comments I want to make with the, so Mark was mentioning like how different features will have an impact that is higher than their own tolerance, I would say. So it projects an error. We could, I mean, we've put some weighting here, but there's other features that might have, we could have put also. I mean, you can imagine on the lower, the upper arm, where it is bolted to the subframe. If that specific hold position is either is in a certain, in the Y direction, it is further, it will make the rotation also on the knuckle at the end. So all these things, and it could be also an angle or something like that. So will have impact that are some of the time maybe greater of than what is on the drawing itself. So this is where it gets more complicated. So I wanted to make a point of this because what's coming up in the presentation, you'll find out that tools exist for that. And when I say tools exist for that, we are using different software to do that. But and also in the next slide, Mark, if you go to the next slide, for what is statistical or probabilistic, actually there are tools also that exist for that. Let's say Polyworks will allow you to make CPKs and kind of a statistical measurement. So if sometimes if you want to do, I mean, this is really nice theory, but then sometimes it gets to the point where, well, do I have any data so how can I select the 1.5 for my expanded statistic? Well, you have to know a bit maybe the bias you have on your different manufacturing processes, and then measuring your components using different type of equipment to do that. Metrology equipment will help you define some certain bias. So if maybe your curve or your normal curve will always be on the left side for certain processes, or more on the right side, or you might have a trend also where as when your tooling is wearing, so as when you're using it more and more, it tends to wear. So could be for hold positioning and everything, but then will tend to go on a certain side of the graphic somehow. So this is where data comes into play, and you can use experience to input into your variation model. So that's what I want to say. I just want to say that when it gets more complicated, software exists to help you solve that. So the theory stays the same, but then you get more data to feed more advanced tools.
That's a really good point, Martin, because I mean, using the statistics, I mean, you need to validate some assumptions behind this. And if you have, let's say, sometimes people say, okay, I have a new design, I don't have any data on actual parts, yeah, but most of the time you have, let's say, some similar parts that you use on other projects, on other products. And if you have the data or the measurements from those parts, then you can use this as the initial assumptions for your new design. And this is where the statistics, this is where you get confident with your statistics, is you really need to have some data in backup to validate your assumptions. So if I just look at the results with our little example, if you do the stack up at the worst case, we'd get let's say a variation of plus minus 5.6 millimeter, expanded statistics plus minus 3.6, and statistics at plus minus 2.4. So you see what kind of difference you can get between the worst case and let's say in the expanded statistics. So you could look at this, and because let's say you have a red worst case result, you could say, okay, no, this is not acceptable, but you have to take care with this interpretation because sometimes it may be acceptable, meaning that if your assumptions are good with the expanded statistics, then I mean 99.73% of the time you'll be within your requirement. So, or if I reverse the interpretation, one vehicle out of, let's say, about 400 will not be good. So based on your production rate or based on your acceptable quality level, you can decide, okay, we'll take the risk, we'll go forward with this with those values, or we can say, okay, no, let's say for really critical system or really critical assembly operations, let's say, okay, no, we don't want to take the risk. How do I solve this problem? How do I make my things better? And this is where the optimization, let's say, of the design comes into play. You have kind of three options, let's say, to make things better. First one, and this is the first one that most people rely on, is, okay, I'll just change my tolerances. It's true, you can change your tolerances, but you really have to take care not to go past the process capability. You have some kinds of limit that you cannot go further. So yes, it will work in theory, but in real life you will just create, let's say, some high price parts and maybe some non-conforming parts when quality control will inspect them. So this is, let's say, the first opportunity. Second one is really, okay, let's just change the design. And there are several ways to to change the design based on dependent on the product. But for the example here, we had a clearance hole for the bolting of my subframe to mainframe, and we had some kind of big clearance, so we can just reduce that clearance if possible. Once again, and reducing this clearance will allow us to reduce, let's say, the variation or the impact with the on the requirement. Finally, the third opportunity is really change the build sequence. To give you an example here, once again, with our assembly, we know that the upper arm finally had an impact on the requirement. So let's say, okay, we can maybe just add adjustment on those lower arms, upper arms, sorry, and we'll really get the good dimension using a jig. Some care has to be taken because this directly impacts your assembly line. So for example, if manufacturing said, okay, no, we don't want to have a lot of adjustment, we want to put parts all together and it fits first time because we have a high production rate and we don't want to waste time adjusting arms, then this kind of proposal shouldn't be, let's say, used. So finding the correct, let's say, solution is really kind of a balance between, okay, process capability, build sequence, and how can I modify my design to absorb as much as variation as possible. And sadly, sometimes, when, let's say, critical requirements, um, you'll find some scenarios that the three of them are not possible. You cannot change the tolerances, you cannot change the design, you cannot change the build sequence, and you still have some, let's say, some risk with your design. And this happens, and this is the, let's say, the starting point of your quality control plan. I mean, based on your tolerance analysis, you have your higher contributors, so you can highlight those things into the drawing and say, okay, those should be really inspected or measured or controlled to see what kind of result I get and to validate that it will work on the assembly. So this is mainly the high steps of doing a basic variation analysis. Of course, all this process, okay, we've made it for one requirement, but the challenge is really to make it for all the requirements on your product. So and try to make all those requirements acceptable before finishing the design. So just to little recap about basic variation analysis. Quick, main benefits really are it's really accessible. I mean, you have a lot of documentation on the different approach. Everybody can start an Excel spreadsheet and start to add the little variation. It's quite a fast method, but when you start to, let's say, add a high volume of requirement, or you want to analyze several scenarios, this is where you start to slow down the process. Because for example, let's say the build sequence changes, then you have to redo the stack up. The tolerance is stack up needs to be updated. So this is kind of a big limitation of this approach. And finally, maybe one last benefit is really by doing this simple analysis, you can, I mean, you'll get the main features that affect your products. So it's really a good tool. Maybe on the limitation side, one big limitation is that you don't have any visual support. You just have numbers that you have to say to visualize yourself and to interpret yourself. So this is a big limitation for the basic variation analysis. I kind of already mentioned this one, management of different scenarios of analysis. Let's say your build sequence change, or you need to add some requirements. You need to each time you add something or change something, you kind of need to update your stackups. And maybe a last one, limitation, kind of seen it, we've introduced it with the projection effects, but when you have a kind of assembly that is really complex, and then you know that you have a lot of angles, there will be some 2D effects, then the calculation using this method may become a little more complex, or and the accuracy of results may also lack because of this complexity. So to improve this is where, let's say, the advanced variation analysis can be used for more complex assemblies, where it is really worth to do the analysis and you really want some precise results. Then you can use some dedicated software to do this the analysis in the 3D environment. Here in Curaform, we are using 3DCS, and the benefits are, first one is, I mean, this is a big one. You have some kind of really good visual support. I mean, you see your parts moving one to the other. You can evaluate if there will be any clashes with the surrounding areas. So this is a really good point, and because of this, you really understand in a better way the 2D effects or even 3D effects, because you can see them and you can interpret, you can evaluate your results based on what you see. And of course, because of this, the accuracy of results comes with it. Limitations, of course, it's way less accessible. I mean, it's a dedicated software that you need to buy, and it also requires some level of expertise in DM and in let's say in the software itself. Like most softwares, like FEA or like a measurement analysis software, there are some parameters to give to the softwares, and if you don't have the good parameters or good inputs, I mean, you can almost make the software say what you want. So you need some kind of expertise with this kind of software. Just to give you a little understanding of how it works, it's a little bit different than the traditional stack up, meaning that it doesn't just add all the tolerances. It's based on the Monte Carlo simulation. The process of the software is really, okay, you take all your parts and you will apply some tolerances on the critical features that you have. So for example, I have my lower arm over here. I have a position of the ball joint. I'll define the type of tolerance, so a position, but I'll define the range, of course, plus minus, let's say 0.75, like previously. But I'll also define, let's say, a behavior on how do I want the software to deviate this feature. Do I want the software to deviate it in the worst case manner, meaning, okay, in a random manner, it will put it at the maximum and the other time at the minimum? Or do I want the software to say, okay, no, deviate this feature in the normal distribution or uniform distribution or any other, or even, let's say, if you have some data and you have a really specific distribution, then you can make the software use this distribution to deviate your parts within the software. So you'll put all the tolerances to all your parts. And the second, let's say, big step is really to assemble the parts together. And this is where it's important to know how it's assembled. So if you know, okay, I have a bolted subframe to the mainframe, I'll allocate the subframe, but the software also sees that, okay, I have a clearance hole between my subframe and my mainframe, then I have a clearance and my subframe will kind of float onto my mainframe. So within the assembly method, the software can capture those kind of variation, and then finally you'll put your measurements that you want. So we had an example with the wheel position of ±4. So we can, let's say, highlight the surface or put a point over here and say, okay, I want this point to be stay within a ±4 millimeters. And this is where the software gets interesting, because once your build sequence is embedded into it, then you can add all the requirements you want. So if you have, let's say, 20 requirements, you've put your tolerances, then you have one analysis, and you have, let's say, 20 measurement results. So the software for each, let's say, makes the process and repeats this process, let's say, a number of loops that you will define. Of course, you'll define a high number of simulation, like 2,000, 10,000, 50,000. And the important is to have some result that converge to a certain constant. So to give you a quick preview of what you get with the results, I was talking about visual preview. You get a quick glance of what you can have. This is just the front view, but in reality, it's really you could spin around the model and see, okay, how this thing move. And if you have parts surrounding your upper arm and lower arm, you could see, okay, is there any risk of clash? So you really have a good understanding of how everything moves. And then at the right side, you get at the top, you get your results. You have your distribution, which is, let's say for this simulation, I've made 10,000 runs. So at each run, the software took the measurement, it compiles the result into an histogram and shows you, okay, variation of your requirement, at the worst case, you have a plus 5.9 to a minus 5.5. And because of the random manner, even if it's a worst case analysis, I mean, the software didn't put all the parts at the maximum at the same time, and it didn't put all the parts at the minimum at the same time. It really goes in the random manner and compiles this at every loop. So this is where the number of simulation is really important, and this is why you get this nice bell curve because of this random manner of the software. So you get your, let's say, your min and max out of 10,000 run, and at the bottom you also get your list of contributors or critical tolerances. So if we look at the first one, I mean, the part is a lower arm, which is the red one. It's the ball joint position, which has a plus minus 75 millimeter range or tolerances. And you see the contribution that is related just to this tolerance. I mean, 32% of the total variation. So if you have a modification to do, I mean, this lower arm needs to be way much precise than plus minus 75. So this is where it's really interesting to use this software. But I mean, the whole idea is quite the same. If you want to optimize the design, you have the three same options. You have one, tolerances, can I reduce them? Second, the design, can I reduce some clearance? Can I change, can I add clearance between parts? Can I change the geometry of the parts to make it more less sensitive to variation? And can I change the build sequence? The difference here is that I can, let's say, simulate those changes into the software and see what will the results get. So by sometimes just a few clicks, you can, let's say, modify the inputs, redo the simulation, and see the updated results. So you have kind of a validation before doing the changes into the CAD. So I didn't see the time running. I've run into it quite, I think, into time. Just to have a quick summary of different points we've seen. First one, just before doing a tolerance stack up, make sure you know first the build sequence, and second, what are the key characteristics? What are really the critical points that my customer or that my assembly line will see, or that is problematic for them. Second point to remember, and maybe this is really related to doing the stack up. Remember to try to always use some physical features, physical and functional features. This is really important. After let's say the tolerance stack up is made, you've made your analysis, you get the results, and you get three ways to optimize the design. One, change the tolerances, but be careful to process capability. Second, change the design, and third, try to change the build sequence. But once again, be careful with the impacts that this can have on manufacturing. And finally, like, be careful with interpretation of the results. Worst case is still a pessimistic scenario. In real life, there's a kind of probabilistic behavior or random behavior of this. So this is where the statistics can give you a more realistic scenario, but ideally get some data to validate your assumptions behind this. So that's it, Martin. I think I went through all the technical portion of the webinar.
You think so? I don't think so. I think there's a few questions in the question box, and we're gonna have to answer some of those technical. Those are good questions. So before we get to the question period, I just want to take 2 minutes to remember our services. Actually, this is the pitch phase of the whole thing, but I'll make stuff on you. Actually, what I want to mention in this portion is pretty much like, depending on the maturity level of your company, there's different ways. If you think that DM has value for you, there's different ways we can help you doing that. Oh, sorry, I closed my camera. I just opened that. So, I mean, it might be just by those webinars. So maybe if some of you will find all the information needed in such a webinar, and that's great, and we'll make some other in the future. But there's also companies that might want, that has certain capacity and just want to have good training on DM and good practices, which we can offer either by directly on site or via web conference. But also mostly what we do with our customers, what we see is that companies have that assemble larger products or even more complex products assembly, what they have issues on production line. So that's kind of how they reach us, where they have issues and they say, well, we want to figure out what's the problem. So we have all the tool set and all the equipment, including metrology tools, to go on site and help them find out those problems. So we do a root cause analysis, and then we'll find out. So it's more like the reverse way of what we think DM should be applied, but still it works. So we'll start from the problem. We'll go up to the root of the issue, and then it goes up to the engineering level. Well, we make engineering changes to the product, so make sure that when it gets back to the production line, we have everything in line. So we'll find the problem. We'll say, well, this is your problem. This is we'll take measurements. We'll have reports. We'll do some variation analysis, and then we say, well, if we change this specific component on the design, and maybe if we have that specific tooling to assemble that at this exact movement, you'll be more accurate on these specific features, and then it will allow you down the line to be more accurate on assembling the final component you want. It could be the body panel, whatever it is, the issue. So, or the doors. I mean, we see a lot of doors issue. When you have moving parts, it's always where it gets hard to fill up the gaps, and you want to make sure that it's sealed. So we see a lot of that. So a lot of 3D variation and gaps and flush and gapness. So we can support also like more onto the engineering portion, I would say, directly on site working with engineering team or intelligent like production team, finding out solutions. So, and we're talking ongoing support. So if your product is already in service and you're finding some issues on the field, so maybe some accelerated wearing on certain component, and you want to find out why you have issues with that, well, we can help you with that. So, and I've seen a question in the question box, what are the software that we use? Well, we can see them right here, which is 3DCS and Polyworks. So 3DCS would be the variation analysis software, where we put all the 3D models and we put up the tolerance and the statistics values and everything in there to make the Monte Carlo simulation and run some simulation on the variation. And then Polyworks, which is more on the data acquisition side, where the metrology tool somehow. So if you want to measure something and then make reports, statistical report, you can work with Polyworks. But there's also other software in the market. This is what we use because we find that those are the more advanced or more appropriate for our needs. But Creform has a VXN spec for basic measurement in terms of measurements, and there's all other solution than 3DCS. We don't resell 3DCS, so it's just a software we use. So I mean, but it's a good one. But if you look out at some DM software in the market, you might find some other, but those are good tools, and we can train you on those tools if ever this is what you're seeking. So so we're pretty much at the question period. There's a few of them. Let me just open back the box. Oh, my box is okay. There actually, Mark, there has been a few questions more regarding the statistical portion, and I just want to actually prioritize them so it makes sense. Actually, well, first question is how many runs did you make on the for the like on the one of the latest slides? I mean, when you were presenting the advanced variation analysis, like how many iterations could this represent, and how much time does it take to to make such a report actually?
Well, a number of iteration is really, for this one, for you see on the screen, you see the number of runs is 10,000 runs. So the idea is to give the software a high level of runs until you reach a certain convergence of the results. It's like if you, let's say, it's a little bit of, just to make a parallel with the IFI analysis, you want to refine your mesh until your results get stable. This kind of software is you want to give the enough runs to, once again, have stable results. And the number of runs is, I think, really dependent on how much parts and how complex is your assembly. So, but I mean, typically we don't go for smaller assembly. 2,000 runs, you start to get some really good results. Now, how much time does it take to make those runs? Once again, it's really highly dependent on the complexity and the number of requirements you want to analyze in your software. But I mean, most of the assembly we've done, we're not talking about days of or even hours of simulation. We're talking about more about minutes of simulations. Once again, if you make a model that is, let's say you have a complete aircraft or complete train within 3DCS, it will take way more time, but and at the same time, your model will be really complex. So to limit this, we prefer, let's say, to split the complete model into systems that are more manageable for the parts, the moves, and everything, and to have a decent number of runs and a decent time of simulation. Because don't forget, you have a time of simulation, but you also have a time to complete the model within 3DCS. So it's really dependent on the, let's say, on the assembly. For the example that you see on the screen, just this requirement, I mean, it's a question of, I mean, 2-3 minutes simulating. It's not for the 3DCS, just this simple model with just that requirement. It's a really simple analysis.
Excellent. And if I get more into the statistical portion, there's a question about well, actually, the first question is, what is a basic criteria to include or not include weight factor in your calculation? So
can you repeat, Martin? Don't
yeah,
think I...
what is a basic criteria to include or not include weight factor in your calculation? So when
Oh, okay, yeah,
when you make the simple analysis, there's the weight factors that you've put in there. So is there a criteria you can use to say, well, yes, I should use such a weight factor, or should I not use that?
That's a good question. That's a really good question, and I'll just go back to this table. So you have the weight factors, but for me, those weight factors are really related on what kind of assembly do you want on your manufacturing line. I mean, if you know that, let's say the operators or you have time on the assembly side to adjust, let's say, the upper arm, and this kind of manufacturing line exists a lot. I mean, you won't consider the weight because you know that the guy can adjust it where he wants. But if you have, let's say, another level of manufacturing line that you want all your parts good, you want to assemble them together, let's say more close to the automotive manufacturing lines. You want your parts all to fit together, and this is where it gets critical to add those weights and to have a good model that simulates what you want on your assembly line. So this is maybe a big criteria to make you choose, okay, am I going to do the complete analysis with all the weights and everything, and okay, all the adjustment, the rotation effects. Let's say if you have a context for this assembly, okay, we have a kind of a slow production rate. We still want the wheel position to be good, but we can still adjust on the assembly line, let's say the rotation of the knuckle, then it doesn't work to put the weights related to this effect.
Okay, and more on the statistical side is, I mean, and I'm not sure we have the correct answer. I don't know, maybe Mark will have, but also for statistical calculation or stack up, which is more relevant to consider CP or CPK? So I guess the question is, when you want to use the statistical results, which ratio, well, is it a ratio or coefficient you should use? And maybe, I don't know, you have the answer for that, Mark? Or
Yeah, I didn't talk about CP and CPKs, but I think what you need is really to consider, those are really two indicators. You need to consider both for me, because they give you two indications. The CP is really the ratio of, let's say, your variation relative to your tolerance interval. So it gives you, okay, does my variation fits into my interval? So this is the first indicator you need to make good. If you have too much variation, that's a problem. Then the CPK considers, let's say, the variation, but also considers the shift into the process. So let's say you have a requirement that is shifted, let's say 2-3 millimeters on one side, and you will get non-conformity. So the CPK considers the variation and the shift into the process. So if your CP is good and your CPK is bad, then I mean, this is not a variation issue. This is a bias or a shift issue. So you really need to look at both together. CPK,
and I think there's isn't it like another indicator, which is CPM, and that includes both, which is more related to the machine side?
yeah, CPM is close to CPK. The calculation is a little bit different, but it's kind of a similar indicator to the to CPK, if I can say it like this.
Okay, so maybe both. Actually, the answer to the question is both are important. That's the point.
Yeah,
CPK
yeah,
and
yeah,
CPK, because you
yeah,
cannot
sure.
just pull out one of the other. It's pretty much both of them. So
Yep,
variation and then bias. So
yep,
it's how much you spread and how much if you're aligned with the I would say no, it's not normal, but the average, or if you shift it from the average. So
exact.
both are important. If I go down, there's a few other questions. What's the name of the software that we answered? So it's 3DCS. How do we know if we, well, let's keep in the statistical portion. How do we know if we need to use a statistical analysis? That's a good point. When do we need to use a statistical analysis? Is there any criteria for that?
Yeah, I think first one is really what is the risk related to the system? I mean, if you have a highly critical system, let's say you make airplanes, or you make airplanes engines. In this field of application, you don't want to take any risk. So this is a criteria, the risk related to a failure with your assembly. The second one for me is, let's say, the production rate or the cost associated with something that doesn't fit on the line. Like, for example, let's say you have a part, you want to assemble it. You have a body panel, you want to assemble it onto a frame. This is an automated assembly. Okay, what happens if this thing doesn't fit? Does the line stops? If the line stops and you have a high production rate, I mean, the cost associated with that non-conformity is really critical. So you'll try to go more on the worst case side. On the statistical side, I mean, if you have, let's say, good knowledge of the data, and you have, let's say, you know that you can compensate in other ways, and the statistical analysis is really a good one, because the main benefit of using the statistical is that you'll be able to give some larger tolerances to your parts, and let's say the functionality of the product won't be that much affected. So it's really a kind of a balance based on, okay, what kind of design are you working on? What kind of assembly line do you have? And I mean,
The cost
what
of the
kind of,
risk.
exactly.
Yeah, it all comes down to money also. It reminds me that for earlier on in the presentation where you said we said, well, sometimes there's no way you can I mean, you cannot change the tolerance, you cannot change anything. And the thing is,
Yeah,
sometimes you cannot really, but it's the cost of it being too high, so that you want to track it by measuring it, because measuring
yeah,
it will become maybe less expensive than trying to make something so much tight into tolerance that the cost would explode for that specific component. So
yeah,
you say, well, let's just track it, measure it, and use statistics to make sure we control the whole process.
yeah.
So we're not control how we can play with that tolerance, but we can control the process. So at least we are sure we're gonna be good, like 99.97% of the time. So that's, and which could be okay, and then you can evaluate the cost of that. So I mean, it comes that to maybe that portion. Well, go
Go ahead,
ahead.
Martin.
No, go ahead. I mean, I was just
Yeah,
seeking.
I was just going to say, just to finish on that question, I was going to say sometimes in the early design stage, I mean, you don't have that much data, you don't know. I mean, if you have nothing, no data from suppliers, no data from other products, I mean, you're blind. Of course, you want to use a worst case, but you can always look, let's say, at the statistical result also to see, okay, am I really bad or am I good? And when things get more problematic, I mean, okay, we have few requirements, let's say that doesn't pass the worst case, then this is where you can evaluate, okay, can I use a statistical on this one? Can I talk to suppliers to have some data? Can I evaluate the risk on my line and then decide if I go with the statistical or the worst case?
Yeah. Okay. There's a thank you. And there's a participant. I want to go back to the slide with the three options. And that's, I guess that's the one with the statistical expanded, and not well, I'm not sure. I think
Okay.
the three options. Oh, well, that's a good question. I don't know. Maybe it's the three option. Yeah, you're right. Maybe it might be this one. It's not clear. And so if maybe the person that wants to see that, if you can ask the question more specific to that slide. So either this one or the slide with the three options of how to use the worst case, the statistic case, or expanded statistic case, then ask a question towards that. We might answer that. Or come back. Yeah, this is, yeah, this, I think that might be the one, that the three option. That's where you have to take a decision on which one you're going to use, and depending on how conservative you want to be somehow, or how what's the risk. When we just mentioned that, how what's the risk of that specific of failure for that specific dimension.
Maybe
Then
one more point that comes into my mind, Martin, regarding worst case or statistics. There's another scenario we see oftenly. There's a lot of assembly lines, let's say, that they're not fully automated. It's still, let's say, people putting parts together, operators with a lot of knowledge. But I mean, those people, if you know that they have, let's say, all the parts they have a lot of parts, let's say, accessible directly at the workstation. I mean, the statistics is saying, okay, if one part fits, okay, just put it back into the bin, take another one, and try to fit the other one. And this may be some kind of reality that makes you say, okay, I'll use the statistics. It's not like this everywhere, but there are some places that it's like this.
yeah, well, independence, the maturity maybe on the company, or there's maybe a last question I'll take is it better to wait until the design is almost completed before starting the analysis, the dimensional analysis? Well, that's a never-ending question, but it's the answer, I would say, in our opinion, it's got to be no. Mark, maybe you can have a comment on that.
Yeah, no, I think you need to start to consider this thing quite early in the design stage. I mean, sometimes even before doing any CADs, let's say you can sketch some concept. Okay, what are the parts? What are the manufacturing processes? What kind of requirements? And already start to evaluate. Okay, am I going to let's say have good requirements or acceptable variation? And I mean, even in 3DCS, we showed a lot of CAD because it's a big benefit of the software, but let's say you have some preliminary geometry, just points, lines, or sketches, you can already start to make those lines and points vary or deviate into the environment and see what would be the impact. The sooner the better, I would say, because as soon as you get the problems, you can modify your design in consequence.
Yeah, I think that's the thing, and that's not an easy portion. I mean, every cross-functional expertise in a company are not that easy to make it work with everybody. So, I mean, you have to consider dimensional, but you also have to consider stress or the part cost or the material use. So there's different design criterions you're gonna have to face. DM is part of one of them. So, and since it touches the assembly, it touches pretty much sometimes the whole product, the whole vehicle. So I mean, you're stuck with having people that are more that will take time to look specifically at these dimensional items. But it's there's and we had a discussion a few days ago with Mark, and because in the first presentation we had those like the pie with the 6 different steps, and in this the presentation today, the pie is the items are not in the same order. And I said, Mark, well, it's weird, since I mean the last one you said, well, there's no last one. It's there's no beginning, there's no ending. It's a process that you can do variational analysis at every step of the process. There's either when you're designing, but also once the product is in production. So you might need to make measurements. Of course, you're gonna make measurements once the part exists, so that needs to be done a bit further on. But then once the product is in life cycle, maybe you're gonna take measurements and then do some more variation analysis, then do a redesign. So it's not something, it's not sequential. It's something you can do at every stage of the product life. So it's not like a full sequential product development. It's pretty much iterative. So well, that's it. So I think that's pretty much it. We answered all the question we had. Hope that was instructive for the people participating. We're really glad to have a good level of interest for our webinars, and we'll keep you posted with the link to the video of the recording of this webinar, and also look out for some more webinars coming up on the same topic or similar topics in the few coming weeks or months. We'll keep that going on for a while, and also with the COVID going on, it might be more frequent. So hope you guys are safe, and hope we're gonna see you next time on another webinar. Thank you for coming.
Thank you.
Bye bye.